Good morning, everybody. First of all, I would like to thank the Yambo team for inviting me to give this lecture on non-equilibrium Green's function theory. Let me say that it's almost impossible to give a comprehensive overview on non-equilibrium Green's function theory in half an hour. So what I would like to do is just to give you a very brief introduction on why non-equilibrium Green's function is a good method to study theoretically non-equilibrium quantum systems. And I will illustrate a little bit what are the merits, but also the problem of this method. And then I would like also to spend some time to illustrate what is the state of the art of NECF. So what we can really do nowadays in 2023 with non-equilibrium Green's function theory. Okay, so first of all, what is the problem that we want to address? So we want to be able to simulate many body systems made of electrons and nuclei out of equilibrium. So the typical non-equilibrium situation that is studied in the experiment is the so-called pump probe setup. In this kind of experiments, you have a system, whatever you want, can be a molecule, a solid, two-dimensional material, initially in the ground state, so very happy to stay in the lowest energy state. And then you excite the system. You perturb the system with typically a laser pulse called pump, then brings the system out of equilibrium. It brings it to an excited state, or more precisely to a linear combination of excited states. Now, in this situation, the system is very unhappy because there is a large excess of energy, and this excess of energy initiates a complex dynamics of electrons and nuclei that want to minimize this, to relax this excess of energy. Fortunately, from the experimental point of view, we have many methods to track, to monitor the evolution of the system in real time. We can study the system with, for instance, optical spectroscopies, like time-resolved absorption, time-resolved transmission, or also electron spectroscopy, like time-resolved, angle-resolved photoemission spectroscopy, also time-resolved photoluminescence. So these are the kinds of experiments that we would like to simulate and we would like to interpret with theory. Okay, so on a very general ground, we can say that the evolution of the system can be divided in two main regime. The first regime is called coherent regime that is established right after the photoexcitation. In this regime, the motion of electrons is really ultra fast because it follows the oscillations, the coherent oscillations dictated by the laser pulse. In this regime, you have very large oscillations in the polarization of the system, which is the induced electric dipole. But this polarization, after a while, after a few tenths or a few hundred of femtoseconds, depending on the material, goes to zero because of essentially electron phonon scattering, but also because of electron scattering. So the phasing is a complicated process. And so you enter in the second regime, which is the incoherent regime, in which the polarization is zero, the dynamics is much. And in this regime, you tend to relax this excess of energy. So what about theory? So the coherent regime can be described quite well with time-dependent density functional theory. And let me say that the DDFT captures very well important effects like, for instance, the induced fields. And in terms of induced field, you can study nonlinear phenomena, high harmonic generation, and so on. You can describe the coherent motion of nuclei induced by the electron-nuclear coupling. You can also address Floquet physics, that nowadays is a very hot topic, and so on. But you cannot describe the decay of depolarization, essentially because the TD-DFT is not capable to describe efficiently the energy transfer between the electrons and nuclei. So you cannot follow the evolution of the system from one regime to the other one. Fortunately, for the incoherent regime is the realm of another method, which is the Boltzmann equation. And with Boltzmann equation, which is a completely different method, nothing to do with TD-DFT, you can describe very well the decoupled electron phonon dynamics. You can also study carrier scattering, carrier relaxation, and also the heating of the lattice because of this energy exchange between electrons and nuclei. But what you can't do with this approach is to follow the dynamics of the system from one regime to the other one. So, and it is exactly here that non-equilibrium Green's functions enter in the game, because I will show you that NECF is capable to describe all the regimes in the, that occur in the temporal evolution, and on top of this, so capture all the effects captured by TD-DFT and Boltzmann equation, and on top of this, also capture new physics, new effects, like for instance, that are not as accessible to the other methods, like for instance, the creation of accidents in real time, but also the dynamical screening of the Coulomb interaction, which is a very, very important process that occurs. And in the incoherent regime, NECF is able to capture non-Markovian effects in the carrier dynamics, which are also very, very important. And also, for instance, the coupling between accidents and coherent phonons, that is something that is measured in the experiments. So, let me, first of all, summarize a little bit the essence of the Green's function theory in equilibrium. So, Gianluca yesterday gave a very good overview on this topic, so I will be very, very fast here. So, let me say that the essence of Green's function theory in equilibrium is the Dyson equation. The Dyson equation is an equation to calculate the one particle Green's function of the system that at zero temperature, for instance, is the time order Green's function. So in this equation, there are some factors. So G is our unknown quantity that we want to calculate to extract physical quantities. And G0 is the non-interacting Green's function, is a quantity that we assume to know, and we know how very well how to calculate G0, so it's not difficult. And there is also this other object, mysterious object, which is the self-energy. The self-energy is in principle something that we don't know, but the beauty and the power of the Green's function theory is that it is possible to expand this unknown quantity in power series of the one particle Green's function. And another very beautiful aspect of this is that each term of this expansion has a clear pictorial representation in terms of Feynman diagrams. So that clearly is telling us what is the physics contained in each of these terms. Now, obviously, depending on how many terms you include in the self-energy or which term you select, the approximation that you do for the self-energy, because in general it's not possible to sum the whole series. So the approximation that you do can be more or less accurate. But here the important take-home message is that the self-energy, thanks to this power series, is a functional of the Green's function. So this means that the equation, the Dyson equation, is closed, even if it must be solved self-consistently. So now let me say, what is G as a function of the frequency? Is nothing but the Fourier transform of the Green's function in the time domain. In the time domain, the Green's function is in general an object that depends on two different times, t and t prime. But now the simplicity and the advantage of being in equilibrium is that the Hamiltonian doesn't depend on time, it's constant. And this allows us to write g t t prime as a function only on the time difference. So de facto, the Green's function in equilibrium depends only on a single variable. So to summarize, the Green's function in equilibrium has only one unknown object to calculate, which is G, that depends only on a single variable, which is the time difference. Now, let's move out of equilibrium. Out of equilibrium is very different because we have the pump field, the laser pulse, that depends on time. So the Hamiltonian is not constant anymore. And this means that now the Green's function depends on two times. G depends on t and t prime. There is no way to cast the problem in terms of a single variable. It's impossible. So, and this is a big price to pay. You see, so you have to calculate an object that depends on two times. Now, the other difficulty, the extra difficulty, is that if you try to write an equation of motion for this G, you immediately realize that it is not closed in terms of one single Green's function. You need two Green's functions, not only one. And Gianluca yesterday gave an excellent overview on this. So essentially what we need is a lesser Green's function that describes essentially the propagation of electrons, but we also need another Green's function, which is G greater, that describes the propagation of holes. And both of these guys, again, depend on two temporal variables. So now we have all the ingredients to cast the equation of motions for these two objects. These are the famous Kadanoff-Bohm equations, and they are the essence of the non-equilibrium Green's function theory. And all the entire non-equilibrium Green's function theory is devoted to the solution of these two equations, which is far from being trivial. So it's a very difficult task. So now, what are the ingredients of this equation? So first, we have an easy part, which is essentially contained in the Hartree-Fock Hamiltonian. So the Hartree-Fock Hamiltonian is nothing but the sum here of H0, which is the one particle Hamiltonian, where there are no interactions. Then is the sum of the non-interacting Hamiltonian plus the light-matter interaction that contains the pump fields that depends on time, and plus the so-called Hartree-Fock potential. The Hartree-Fock potential is nothing but the sum of the first two Feynman diagrams in the power series of the self-energy. So are the first order diagrams. The first one, the tuple, is called Hartree potential, while the second one is the exchange one, is the Fock potential. But this is the easy part of the story. Now, the difficult part comes from the right-hand side. The right-hand side is called collision integral, and is cast in terms of the self-energy that contains all diagrams beyond the first order one that are already contained in Hartree-Fock. Then, obviously, a difference with the equilibrium, now we have two self-energies, obviously, sigma lesser and sigma greater, that depends on two times, again. But again, the beauty and the power of the non-equilibrium Green's function theory is that even out of equilibrium, you can expand the self-energy in power series and draw Feynman diagrams where the building blocks are G lesser and G greater. So these are closed equations. But of course, what about their solution? So it is obvious that their solution is very expensive from the computational point of view, because we have to propagate an object as, say, two objects that depends on two times, and on top of this, there is a minor integral. So in order to know the situation at time t, we have to integrate all over the previous times. So at the end of the day, we realize that the solution of the problem scales like t cube. So this means that if this capital T is the maximum time that we want to reach with our simulation, that can be of the order of, say, some picoseconds, so the simulation, the cost of the simulation scales like t cube. This is a huge cost. So imagine that TD-DFT and Boltzmann equation scales linearly in time. This cubic dependence makes impossible to solve this equation for realistic systems. It's impossible. So now, at this point, we have two options. Or we close the book and we go home and we give up, or we try to solve this problem somehow. So it is obvious that we need some idea to make progress, to reduce the scaling. So now the first observation is that the knowledge of the Green's function at different times is really not needed, because if we want to calculate the time-dependent average of any one body observables, we only need, as Gianluca explained very well yesterday, we only need the lesser Green function at equal times. We just need the lesser Green function at equal times, G lesser TT, and the trace, and make this trace or the observable that we want to evaluate. And if we know G lesser at equal times, we can calculate essentially everything. We can calculate electron density, we can calculate current density, polarization, magnetization, and so on. So please notice that if you take G lesser at equal times, apart from factor minus I, you have nothing but the one particle density matrix of the system. So the first observation is that the knowledge of the density matrix only is enough to our purposes. Now the obvious question is it possible to write an equation of motion for the density matrix only? It is a quantity that depends only on a single time. So the answer is yes. It's very easy to derive an equation of motion for rho, because you just have to take the two Kadanoff-Bain equations of the previous slide, set t equal t prime to sum these equations, and you end up with this very beautiful equation for rho. Well, again, there is the R3-Fock Hamiltonian, as before, entering in a different way, because now you have a commutator, but who cares? And then there is also a collision integral. So the equation, although it's beautiful, is not useful because it's not closed. Because you see that even if you know the self-energy, but you don't know the self-energy in general, there is still an explicit dependence on G lesser and G greater. While the only unknown quantity that you would like is the density matrix. So now, how can we close the equations? So the idea, is to make an approximation not on the self-energy, is an approximation on the shape of the Green's function. We can approximate G lesser and G greater in terms of the density matrix, which is the only unknown quantity that we want, and in terms of the retarded and advanced Green's function. But since we want a closed equation, we further approximate G retarded and G advanced as exponentials of the R3-Fock Hamiltonian. And since the R3-Fock Hamiltonian is a functional of the density matrix only, the equation close, and we can solve them in our computer. Please notice that under this ansatz, which is called generalized Kadanoff-Bain ansatz, the computational scaling is reduced from cubic to quadratic, and this is a huge gain, and this allows us to study realistic systems, as I will show you in a second. First, let me do a remark on this equation that we are going to solve. So first, as I told you, there is the commutator of the density matrix with the R3-Fock Hamiltonian, and this is mainly responsible to dictate the evolution of the system in the coherent regime, while the collision integral is mainly responsible to dictate the system dynamics in the incoherent regime. Let me say that as David will explain, I guess, tomorrow, this first part of the equation, by neglecting the collision integral is what is currently implemented in the Yambo code, while in our code, which is called Cheers, and Jaroslav Pavliuk will give a lecture on it on Thursday, and a couple of tutorials on Thursday and Friday. This code is possible to include both terms, both the coherent part included in the commutator and the incoherent part included in the collision integral. Okay, so let me first show what we can do. We can study with this equation. We can study, for instance, the ultra-fast electron dynamics in organic molecules. So for this kind of systems, let me say that the second order self-energy is enough. So this means that we include the first 4 Phonon diagrams in the power series. We also can assume that the nuclei are fixed, don't move, because we are interested, as you will see, in a time scale which is so short that the nuclei don't have time to move. So we can approximate the nuclei as fixed. And please notice again that the scaling, within this approximation, the scaling is quadratic in the temporal evolution. So let me show what we can simulate in practice. We want to study the charge migration in anorganic molecules, which is the phenylalanine, which is an amino acid. And what is charge migration? Charge migration is a very interesting phenomenon that occurs in a molecule, typically a big molecule, when you ionize it. So you remove an electron from this molecule by illuminating with the system with a pulse. And in this state, the system is very unhappy, and the electrons start move from one side to the other of the molecules. So along the molecular backbone. And this is exactly charge migration. So in this very beautiful experiment, which is probably the most famous experiments for ultra-fast dynamics in molecules, the experimentalists were able to measure the frequencies of this oscillating motion as a function of time. And you see that in the experiment, you see that right after the ionization, the motion is characterized by two frequencies, and after about 20 femtoseconds, the behavior from bichromatics become monochromatic. So the motion is characterized by a single frequency. So this is what you obtain with time-dependent density functional theory. You see that the result is qualitatively correct, but indeed not so good. So in particular, you are not able to describe this low energy, so low frequency component of the motion. While with NECF, you see that the result is really much better, is indeed spectacular. So this means that all non-Markovian effects missed by TD-DFT are necessary to reproduce the experimental behavior. Okay, we are very happy, but indeed not so much, because we want more. We don't want to study only molecules. We want to study extended systems, so solids, two-dimensional materials. And in these extended systems, you know that the second-born self-energy, the second-order self-energy is not enough. And is also not enough to consider the nuclei fixed, because there is the important electron-phonon coupling. So in particular, we want to replace the second-born self-energy with the GW self-energy, which is the correct self-energy to describe solids, so in particular semiconductors. And we also want to introduce the so-called Fan-Migdal self-energy. The Fan-Migdal self-energy describes essentially the scattering of one electronic state to another electronic state through the absorption of emission or an emission of a phonon. And On top of this, we want to reduce the scaling from quadratic to linear, because we want a competitive approach with, for instance, TD-DFT or Boltzmann equation that scale linearly in time. So in practice, we want more and pay less. So you understand that the challenge is huge. So let's see what we can do. So first of all, let me draw the self-energy that we want to study. Is the sum, as I told you, of GW plus phamigdal. So by looking at this self-energy, you immediately see that there are new actors in the game. So there is W, that is the screened interaction that obeys this Dyson equation that Gianluca described very well yesterday. But there is also a new vertex in the theory, that is G, the electron-phonon coupling. And there is also this spring line in the phamigdal self-energy, which is the phonon Green's functions. So this means that if we want to study electron-phonon coupling, we have to propagate not only electrons, but also phonons. And D obeys this other Dyson equation. And there is another auxiliary quantity, which is the polarization, that you can see immediately is very useful to calculate both D and W. So now, if we write down the equation of motions that we need, of course, we need to propagate rho according to this equation, as we did before. But now the collision integral contains these two self-energies. And on top of this, we have to propagate W, that out of equilibrium depends on 2 times. And we have also to propagate D, the phonon Green's function, that depends on 2 times as well. So we see that at the end of the day, the scaling, if we want to do GW plus phamigdal, the scaling is again cubic, so a disaster. So again, so we have 2 possibilities again, or we close the book and we go home, or we try to cure this problem somehow. So let's see what we can do. So now the first idea to make progress is to treat electrons and phonons on the same footing. So exactly like we did for electrons, we didn't propagate the 2 times Green's function, but only the density matrix. For phonons, we want to do the same. We want to calculate only the phonon density matrix, rho. And if we sum the 2 Kadanoff-Bain equations for the phonon propagator, or take T equal T prime, we end up with this equation of motion for the phonon density matrix only. So as before, we can expect that this equation is not closed, because the collision integral still depends on D lesser and D greater as before. To close the equation, here we come with a second idea, to make a generalized Kadanoff-Bain ansatz also for phonons. So we express the phonon Green's functions in terms of the phonon density matrix, gamma, and in terms of the retarded and advanced phonon Green's function. And to close the equations, we approximate D retard and D advanced as exponential of the mean field phonon Hamiltonian, which is a functional of the phonon density matrix only. So now the equation finally closes, and we can solve with the computer. What happens? So first, let me say that, these are the 2 coupled equations now that we want to propagate to evolve simultaneously electrons and phonons interacting among each other. But there is a subtlety here, that these equations indeed are still not closed. Because if you write the Hartree-Fock Hamiltonian now, because of electron-phonon coupling, it acquires an extra term, which is called Ehrenfest potential, that depends on the coupling of electrons with the classical displacements of the nuclei. So, and it is obvious that to close this equation, we need an equation of motion for the displacement field phi. This is not difficult to derive. This is the equation. Oh, sorry. This is the equation of motion. This is a linear that scale linearly in time. It's a scalar equation, so very easy to solve. So at a negligible extra computational cost, we have also the Ehrenfest dynamics. So we are very happy. We are very happy because now we have a closed set of equations of motions for the electron density matrix rho, the phonon density matrix gamma, and the classical nuclear displacement phi. Closed equations. We are very happy. We start to implement them, and we realize that the scaling is again cubic. Disaster. So at this point, must be really depressed. So we did a lot of effort with because simulating, so propagating only one-time objects, making the generalized pattern of Bayes-Mansatz is not enough. Doesn't reduce the scaling. So how do you do? So it is clear that at this level, a revolutionary idea is needed. So what I'm going to illustrate in the next slides is something really new. It's stuff of the last 2-3 years, in which I will show you how it is possible to reduce the scaling of this equation from cubic to linear, and so become really competitive with the other approaches. So what's the idea? These are the 3 equations of motion that we want to solve. The first one is easy because it's already linear. The problem arises from the collision integral, the 3 collision integrals in the last 2 equations. So now the idea is to recast the collision integrals not in terms of the self-energy that requires some memory integral that kills you, but in an alternative equivalent way, which is cast in terms of higher order Green's function. Indeed, this is something not new because it is something known since the old times, and it is known as Martin-Schwinger hierarchy. So in practice, you write the GW collision integral in terms of this calligraphic G, which is a two-particle Green's function, and you write the von Migdal and the Phonon collision in terms of another higher order Green's function, which is a polaronic Green's function. Now, at this point, we didn't gain anything because the calculation of this calligraphic G is a mess. So, but the miracle happens when we do the generalized pattern of Bayes-Mansatz, both for electrons and for phonons. We realize that the equation of motion for this higher order Green's function has a right-hand side that depends only on the instantaneous higher order Green's function and on the instantaneous density matrices. This means that thanks to the generalized pattern of Bayes-Mansatz, the scaling is finally linear. Very good. So just to summarize, these are the equations of motion that we have to solve. There are for 5 objects: the electron density matrix rho, the phonon density matrix gamma, the Ehrenfest field phi, and the 2 higher order Green's function G. But the scaling is linear. Let me say that this set of equations constitute the state of the art of non-equilibrium Green's function theory. And their solution allow you to simulate in real time the evolution of correlated electrons and nuclei. It gives you also access to the Ehrenfest dynamics. This means that we are able to simulate the oscillation in real time of the nuclei. And very important, here I couldn't spend time here, but this is a conserving scheme. Conserving scheme is something crucial. This means that the conservation laws are fulfilled during the temporal evolution. And this is a very, very important property. If you want to do real time, you must be conserving. If energy is not conserved, it's a disaster. You completely lose the control of what you are doing. And these equations are conserving. From the numerical point of view, we have implemented this set of equations in our code, which is called Cheers. And I would like to spend the last minutes to show you an explicit applications of what we can do. This is something very, very new. And we have studied the real-time dynamics in molybdenum disulfide monolayer. You know that this material is a little bit the holy grail of transition metal dichalcogenides, is probably the most studied materials in the last 10 years. And so just let's see what happened with NECF in this case. So we consider the system initially at Kelvin. We studied the temporal evolution initiated by a pump pulse of, an ultra-fast pump of 15 femtoseconds, and with a frequency such to excite carriers from valence to the conduction band, so an above gap excitation. So first of all, let me show what I promised at the beginning of the talk. So how we can describe the transition from the coherent to the incoherent regime. So you see that here there is the polarization as a function of time. You see that it decays to 0, as it must be, because of electron Phonon scattering. But it is also very beautiful to study the decay of the polarization. This is a log plot as a function of the excitation density. And if we extract the time scale for this decay as a function of the excitation density, we see that this can be very nicely fit with this power law, which has been predicted long ago by Haug to be a universal power law dictating the dephasing, so the decay of the polarization in both 2D and 3D materials. And we nicely see that our simulations are perfectly consistent with this prediction. So, but we can also address carrier dynamics. So carrier dynamics is here very complex because you excite, so the pump first excites carriers from the valence band to the conduction band. And since you have a large excess of energy, you can enjoy intra-valley scattering in which the carriers migrates, electrons migrates to the bottom of the conduction band, and at the same time, holes migrate to the top of the valence band. But the system is such complex that you can also have different processes called inter-valley scattering, in which the carriers that you initially create in the K valley of the material migrate to another valley, which is for electrons is called sigma valley, and for holes is the gamma valley. So in our simulation, we reproduce very well this kind of scattering. You see that as a function of time, the different valleys become colored, and this is a process mainly due to electron Phonon scattering. So this is the job of the fan-Migdal self-energy. Okay, here I simply show you how the carrier density in the different valleys evolve as a function of time. But it is also very beautiful to see how a Fermi-Dirac distribution is created in time. So at the beginning, you see that the distribution of carriers as a function of energy is highly non-thermal because the pump creates spots, well-defined spots in the frequency space that are formed from being a Fermi-Dirac. But as time flows, you see that the system relaxes to a quasi-thermal Fermi-Dirac distribution. So, what about Phonon dynamics? Phonon dynamics is very useful, for instance, if we want to simulate the heating of the lattice. So, this is how the lattice, the effective temperature of the lattice, evolve in time for different excitation density, for different pump fluencies. And you see that the larger is the excitation density, the larger is the final temperature that we get. And let me say that for very high excitation density, 10 at 14 cardias per centimeter square, our results, the NECF results, agree perfectly with the Boltzmann equation prediction. So, because at about 400-500 femtoseconds, the system enter in the incoherent regime where the Boltzmann equation is very good. And so it's beautiful to observe that NECF is in perfect agreement with Boltzmann. Finally, let me just show you that even here we plot an effective temperature. This is an average over all the first B1 zone. But if you zoom inside the different zone, you see that even if the temperature is converged to a steady state value, the temperature distribution of the B1 zone is highly anisotropic. There are still hotspots, signaling that there are phonons that are more coupled than other ones. And last but not least, we can also see how the nuclei move in real time. So this is how the oscillations of the along two normal modes, so longitudinal optical and transverse optical mode of the material, evolve as a function of time. And we see that the nuclei oscillates coherently even when the electronic bath now is completely incoherent. Here we are in the incoherent regime, but the nuclei still move coherently. So this means that the nuclear coherence survives much longer. So with this I conclude, and you can have a look at these references if you want, if you are interested in the topic, and I thank you very much.
Thank you, Enrico, for the very nice talk. So the session is open for questions, please.
Thank you for a very nice talk. My name is Stefan from the Oldenburg University. I have a question regarding the generalized Kadanoff-Behm ansatz. So, if I remember correctly, you mentioned that we reduced the scaling through that ansatz in the end, but once again, if I remember correctly, the exponential has also a time integral inside it. So, where does the reduction come from?
So, no, it doesn't work, but maybe. Okay. No, yeah, no, it doesn't work, but don't care. No, no, the time scaling with this exponential that I showed you before is not affected because, okay, this is a bit technical point, but indeed, what is important is the time derivative of this integral, and the time derivative of this integral depends only on the instantaneous artifact Hamiltonian. So, but I admit this is a bit technical point, but believe me, it doesn't affect the scaling.
Okay, thank you very much.
Because only the time derivative of this is actually needed.
Thank you.
Other question? No other question? So I have, I have one. Could you comment about your equation on equilibrium green function approach and the approach used by Malic, the block equation? I mean, there are all these paper of the group of Eric Malic on 2D material. So I would like if you can do a comparison. I mean.
Yeah. No, of course, the difference is huge for different reasons. First, the main one I would say is that if you write an equation of motion, so you have in mind this equation of motion for the accidents, for the accident population, right? Yeah. These equation of motions are valid only in the incoherent regime. So you cannot describe the coherent evolution of the system with this equation. Second, these are equations for an object that is a contraction of a two-particle Green's function because it's the accident population. And in this respect, are equations that are perfectly included in our equation because we also include the explicit evolution of the two-particle Green's function. Now, if you take in this two-particle Green's function the right particle Hall channel, you have exactly the quantity that they are.
Okay, we can thank Enrico again.